So Arwen's from Zendesk, and she's going to share some really good experiences about what Zendesk have been doing with ML and deep learning. It's going to be really interesting to hear more sort of case study and experience, actual industry experience about how things happen. Thanks, Alan. Make it feel welcome. Thanks.
Hello, so am I on?
Yeah.
Oh, okay. Wow, there's no feedback up here at all. So my talk is titled Aha Moments Deep Learning Industry. Our broad umbrella team name is Aha, and we just make up abbreviations for anteaters, hate, aardvarks, things like that. But I am from Zendesk, that's me. I'm a data scientist. Does anybody here know what Zendesk is? Hands? Yay! The rest of you, do you know what Salesforce is? We're like Salesforce, but better. So we do ticketing systems, knowledge centers, customer relationship management, things like that. So, for example, if you, if you took an Uber here from the airport for this talk and you left your bag in the Uber and you sent an email or a message through your app, that would go through a Zendesk instance. So we handle all those conversations that you have with companies. We have 7 products. They're all listed there. So we've got standard support, guide, which is like a help center, chat, talk, message, and explore, which is reporting. We have a data team. Zendesk's entire ML capability and team is based here in Melbourne, just over on Queen and Collins Street. And we are far more than just data scientists. So Answerbot, which is the product I'm going to be talking about today, was produced by 2.5 data scientists, 20 engineers, a UX designer, a product manager. We all like gray t-shirts a lot. And we have an oddly bimodal height distribution in our team where we're all very tall or we're all very short, and there's nobody in the middle. Oops. So here we go. When companies come out and they're like, hey, look at this amazing machine learning model that we've got in production, or look at this great breakthrough we've made, it looks a lot like, well, we just did some things and it worked and it went into production and it was all very simple. That's what we want to say in our press releases, that's what we want to say to our analysts that are driving our stock prices. But in reality, underneath that is all of this stuff that often makes it feel like nothing is working and nothing is ever going to work and we're never going to get anywhere. So, Answerbot. Answerbot is my baby. I was one of the 2 data scientists that originally pushed this research through. It was a lot of fun. I'm still lead scientist on Answerbot. Answerbot enables customers to self-serve their own customer service inquiries. So you can imagine people write in a lot of emails asking how they reset their password. I cannot tell you how many times our database contains the phrase, how do I reset my password? Or how do where do I find the size chart for women's running shoes? Answerbot helps with these situations. Pretty simple cases, repetitive queries that agents really waste a lot of time on that they don't need to. They can be easily answered very quickly, and people could move on with their lives. So, what do our statistics here say? Yeah, 76% of us prefer not to have to wait for a human being to get back to us for a simple question. I don't want to wait for the call service to open. Zendesk handles over 1 billion tickets per year, and we have over 100,000 paying accounts right now. So why is this a difficult problem? We have search, right? And we have Google, and they've been doing this forever, and we've got Elasticsearch. It's pretty easy to spin up and run over your knowledge base. But it's not, because we're not dealing with search queries. People don't email a company with keywords. They email a company with hi. we'd really like to dump our ticket data out of Zendesk so we can import it into an external reporting product and identify high-risk customers. Can you help us out? That's pretty much a real ticket, by the way, with personal information changed. And we have an article written for this in Zendesk. But you'll notice that none of the words in the article are in that email. We can't do a keyword search. We can't just run that through a basic Elasticsearch or even a slightly more intelligent Elasticsearch system. It's not going to work. If you went in and searched for data export CSV, sure, it would get there. So that was our problem. How do we take these incoming, long-form, not very well-defined queries and map them to existing knowledge center pages? So this talk is based around our journey through addressing this problem as a pretty new data science team. So the first things first, the first thing you should ever do in any ML project, right after you determine if you really need ML, which I have loved hearing, so many things can just be engineered. Don't go to ML first. It's really not the best way. Try the simple stuff. Vanilla ML, which is the standard things like logistic regression and random forests, they work really well. Like, stupidly well. I did a PhD in machine learning. I spent years developing super complicated, compute-intensive algorithms so that I could go out and have my first job be deploying logistic regression models to production, which is a great deal of what you do in the real world. So, this problem falls under the general class of problems called NLP, or natural language processing. Hands? Anybody familiar with NLP? A few of you, great, cool. So, the short definition of it is, how do we turn words into numbers so computers can understand them? One way to do this is to take your words, to turn them into numbers, like just assign an ID, count how many times they all show up, normalize it for sort of the size of your corpus and the frequency so that you don't think that the word "the" is really important. And then you run it through a logistic classifier, which will give you a score, and that's how you make your decision. So for us, we said, well, we can take our tickets, we can run them through and make a TF-IDF table out of them. And then we can run it through a logistic classifier in sklearn, and that will predict one of our existing articles. So we're just mapping multivariate classification. Example comes in and we give it one of some number of labels at the end. Super effective. About 80% of the time we could replicate human behavior for recommending an article to a ticket. So we're done, right? We've done this. It's cool. 80%, as anybody can tell you, is a pretty respectable multivariate model accuracy measure. So it's accurate, it's performant, it's familiar. Lots of people know what this is. This is not like machine learning magic. This is pretty standard in statistics and analysis everywhere in the world. And it's explainable. We can say, well, like, look, these words came in, and they're very important, and that's how we mapped it over to this label. However, like I said before, we have over 100,000 paying customers. And so for this model, we would have to build, let's say half of our customers took it up, 50,000 individual models. And for this type of model, you also have to have labeled data. So we would have to have about, we figured, 40 tickets that had already been answered with articles before we could build a model which could recommend those articles. What happens if a new article gets written? Knowledge bases are living, breathing data stores. Companies are evolving and changing, and they're adding information in. Well, great, you've got a new article. You know, give me 40 more labeled tickets for that article, and then I'll rebuild the model at some point in the process of the other 50,000 accounts. And then that goes for new customers as well. You know, they we get a new customer and they port their whole knowledge center in, well, it's basically useless for this product until they get some data built up. So high barrier of entry and the cold start problem, which is new customers can't just turn it on. So, unsupervised classification. Do you know what unsupervised classification is? Oh, nice, yes. Okay, so we've got supervised classification, which is I have an example and I know the correct answer. And I can learn from the correct answers how to answer more problems like that. Unsupervised classification is I've got 2 bits of data that are sort of related, but I don't actually know the right answer. I can't feed that into the machine. So now we take our articles, and we take our tickets, and we do the vectorization process again, and then we get out a vector representation of those. So now we've got one set of numbers that means the ticket to the computer. We've got another set of numbers that means the article. And we try to make them very close to each other. Okay, so we pretend that they're coordinates on a map, and we want those to live very near one another if that article answered that ticket. That made a huge difference. We also did some pre-processing, which also made a massive difference. Pre-processing in NLP is things like removing numbers, URLs, email addresses, some stemming, stemming and lemmatizing, which the goal is to reduce words like run, running, and ran all down to run, because that just means the same thing. So after months of research, we had a problem that could handle new articles, didn't require a lot of label data, and was still pretty intuitive. Like, we could still figure out what was going on, it was still explainable. However, we were still faced with building over 100,000 models. And we had sort of hit a wall for performance-wise. We couldn't seem to push it beyond this performance plateau that we had reached. The other thing that you have to worry about in industry that you don't have to worry about in academia is it was slow. People want answers now, not tomorrow. So it was not suitable. So, by the way, we like GIFs at Zendesk. So we did a big pivot. We realized that we had to do something dramatically different. And at this time, deep learning was really making a lot of noise. It was starting to get in the public eye even. My grandmother might have heard of it. So we decided to go to deep learning, but none of us had a deep learning background. We had, I have a background in machine learning. We had somebody who had a background in computational neurology. We had a computational pharmacometrics, and somebody who'd done image classification for medical imaging. So, no deep learning. So the first thing that we had to do is figure out what we were doing. In this realm of new research, what was the problem we were trying to solve? Which is essentially answer the question. We need to answer the customer's question, and then this translates to academic literature as a question answering problem. That was handy with self-naming. We know what it is. Now what do we do? You read a lot of papers. You read all the foundational papers, you read all of the really hot papers that everybody's talking about, you read the papers with all the citations in Google Scholar, and you don't just read them, you go through them paragraph by paragraph, and you do the math, and you talk about them, and you try to understand them. We still run, and we had already run, a journal club where we meet every week as a team, and a different person presents a new paper every week. So this is one of the ways that we keep up. This helped, not by teaching us how to actually do anything, but it gave us lots of ideas. And it showed us the range of possibilities that we had to work with. And it gave us hope that we would be able to solve it. and that we could develop the intuition to become productive deep learning scientists. This is another team favorite. So reading is great, but nobody's learned how to program anything by reading a book. So we spent a week as a team working together, taking the Udacity deep learning course. We went through the TensorFlow examples GitHub repos, and we implemented a lot of stuff from scratch. Now, context, TensorFlow is now at version, who's from Google? Who knows this? I know this. Does anyone from Google know this? What's it at? Point. Yes. 1.12. The points matter in TensorFlow because the world between 0.4 and 0.6 became a completely different place. We started at version 0.6. There wasn't a lot there. We rolled it by hand. And it was very, very frustrating, but we really learned the fundamentals solidly. Because if we wanted a bidirectional recurrent neural network with an LSTM, we had to hand code in TensorFlow base, tf-mult, tf-add, a bidirectional recurrent neural network. Now we use packages. Sorry, that was pretty good. Where are we? Deep learning. Deep learning's magic. It just works. If you have lots of data and a good use case, and you obviously know everything about it, like we did because we had read all the things and done all the tutorials, we were good. Believe not what you read. Not everything works. Even stuff that's supposed to work doesn't. So when we started out on this deep learning journey, this is what we thought. It's robust to poo. It has better performance, and that we would be able to use one model to understand our entire world, and there were absolutely never any drawbacks. So, at this stage, our team split into two, which meant I went one way and my colleague went the other way, and we studied two different deep learning approaches. So I went down the recurrent neural net, the RNN path, and he went down the convolutional neural net, the CNN path, and we investigated these in parallel. CNNs, we still haven't quite got to work the way that some extremely popular people think that they should work on text, but the RNNs did work. So what we came up with is this document embedding model. So we have our articles and we have our tickets. So it is still what we like to call a semi-unsupervised approach. We do some pre-processing. And now we don't do TF-IDF. We actually run a package out of Facebook called FastText. Is anybody familiar with FastText? No. Has anybody heard of word embeddings? Yes. Okay. What's my time look like? Yeah. All right. Word embeddings, in the short form, is a way to take a word and put it in a location in a space so that all of its neighbors are about related things. So if you imagine a 2D plot, words like poodle, Labrador, bagel are all going to be in one spot, where words like Persian, cat, bangle are all going to be in another spot. They're probably going to be very far apart. So fast text is a thing which will consume your text and build this embedding space for you, for your words, so that all the words in your text are sort of clustered by similarity and relatedness. And then we use TensorFlow, which is why I'm here, because we use TensorFlow. We use TensorFlow to consume those addresses and build a concept map of what's in the ticket. So that now we don't just have words that have addresses, we have entire concepts that have addresses. So it doesn't matter how many ways you say, can I reset my password? I can't get into my account. I have been locked out. They all go to the same spot, and that same spot gets mapped to the same spot that the article about how you reset and unlock your account is also mapped. And so when we put in a ticket in an article, we get like a ranking of the articles that are closest and how it answers that. If I have time, I can go into that in more detail for you. So checking in on our assumptions, it's robust to who? No, it's not. Deep learning, no matter how much data you have, is still a garbage in, garbage out system. We've proven it, categorically and repeatedly. We spent 2 weeks just looking at our regex, and we got a 25% performance increase. Nothing else changed, just cleaner data. It is also not robust to invalids data. So, as many of you may have noticed, customer service agents like to sign off their emails with a link to their Help Center's Frequently Asked Questions page. The network learned very well that that was the best answer to always give to every single question, always. And then we also found that we have hundreds of thousands of accounts, but some, like Uber, are bigger than others. And so they would still dominate the language. We still had to balance the data out a little bit. The other problem was missing vocabulary. One of our customers is the Dollar Shave Club. Do you know what Dollar Shave Club is? Yes? Okay. So they send you razors on a regular basis so you can shave. They also have other, mostly male-directed beauty products. We didn't know what moisturizer was. This was a problem. They turned it on. They have lovely Help Center articles about moisturizer. They're getting lots of questions from gentlemen wanting to know how to moisturize their stubble, and we had no idea what they were talking about because we were just throwing it away. We'd never seen it before. So, you do have to care about your data. What else do we have? Better performance. Deep learning is magic. It always performs better than, say, logistic regression. Took us 6 months of extremely, extremely stressful work just to get back to the performance of our logistic regression models. Okay, 6 months working more than I really should have been. My colleague also working more than he should have been, just to get back to what we had already gotten with logistic regression. And there were so many times that both of us were so stressed looking at our team of 20 engineers and a UX designer and a product manager and some senior VP of product who came over from San Francisco to figure out what we were doing with all of his money, that we weren't going to do it. That we had sunk all of this time into it and it wasn't going to go anywhere. It was not going to work. It worked. Just jump ahead. And then the last thing was one model. We did eventually get to better performance. We have a model in production now, driving Answerbot, called MegaMike. It has responded to more than 1 million customer inquiries successfully, which is pretty cool. And it is, in fact, one model across all of our accounts, across all of these different domains. So ride sharing, crafting, retail, industry, education, finance. We have a single model which has a joint understanding of that language. Moment number 4, putting science back into data science. Interestingly, when you work with clinical scientists, like this becomes more important. When your colleagues are people who've like prepped slides and done gene sequencing, you learn a lot more about proper science as opposed to my science, where I just try stuff until it works. So, trackability, you're going to go through lots and lots and lots of models. Even if you don't know what the models are doing and you're just applying techniques and data and different features, you're still going to go through, I'm guessing, 6 of them. You need to be able to track it. You need to know what you've done, what you've already tried, and that there's a few problems with it. I highly recommend GitHub and documenting everything in README files in your experiment directories. Reproducibility, this is science, right? You need to be able to reproduce it. This is also industry or your pet project, which means that when you put it away and you have to go back and fix something in 6 months, you need to remember what you were doing and why you did it. What's my last one there? Oh, reliable. Yeah, it's in production. It has to be reliable. That's the engineer's problem. Not really. It's my problem too. The other reason to make sure that it's trackable and reproducible is that things that didn't work the first time you tried them might work later when you know what you're doing more. When we first started, bidirectional LSTMs did not improve anything. So a LSTM reads over words in order. A bidirectional LSTM reads over them this way and then goes back over them this way. It's supposed to be really good. And it did, finally. But we had to grow a lot before we were able to implement an architecture where that was actually able to sort anything out and help. Metrics. Human in the loop. I couldn't find a GIF of that, unfortunately. Validate your model. What's actually important, okay? All of us can come up with numbers that make us look really good. We all know, what is it, with software engineering, how many lines of code you have written versus how many lines of code actually work at the end of the day. Select a metric that reflects the end use of your model. So it doesn't matter if it's super, super accurate if that's not what you're going for. Be humble and, admit it even if it's really bad. The other thing is, it's really hard to beat human in the loop. If your model is going to interact with humans, validate it with humans. Show them the results and see if they make sense. Somebody earlier said that these problems are pretty much solved for industry. I would argue that's not true. Language processing is not a solved problem for industry. Human emotion and communication is not a solved problem in computing. You are talking to companies that you are spending money with. This is important to you. It's the thing that you want. This is not something that computers understand. It's not a solved problem. It is absolutely novel to every new company that picks it up and tries it. But the underlying techniques and approaches are universal. Keep reading. Just read a lot. Read blog posts. You don't have to go read scientific papers. Read some blog posts. Go do some Google courses. Go do some Udacity courses. It's fun. Research is hard, but it's also fun, I think. This is Zendesk. That's what we do.
Thanks, Alan. That was great. Has anyone got any questions about the journey that they've been on? Well.